One of the most fascinating lessons in mathematics is rarely learned by students who stop studying it after high school, and that lesson is this. The nice objects we spend all our time learning about are the exceptions. So much of our time is spent with integers, nice numbers with no fractional part. Adding, multiplying, dividing, solving equations, integers as far as the eye can see. What comfort, and what illusion. It's not hard to see that the integers are an unusual type of number. They are only a desperate few among the number line, all with great chasms of decimals between them. And so it is with many other facets of mathematics as well. In calculus, we learn about derivatives of functions. This function goes down, then flattens out, then goes up, so its derivative is negative, then 0, then positive. Of course, some time is spent on functions that don't have derivatives. Thomae's function, for example, is a famous function that is not differentiable anywhere. It's also sometimes called stars over Babylon, and its graph looks something like this. Turning it upside down, you can see why it's also sometimes called the raindrop function. These cool names for this fascinating function inspired this design, which is available on t-shirts, hoodies, mugs, and more, only at mathshin.com, my math fashion brand. The design features Carl Thomae in front of Babylon, with his umbrella held up against the raging Thomae's function storm. Again, it's only available at mathshin.com, link in the pinned comment and description. We also have more minimalist designs like the 17 square optimal packing pullover and more. There are no cooler math shirts available anywhere in the world, so check it out if you want some swag and to help support the channel. Regardless, you can see this non-differentiable function is a bit trickier than classics like x squared and sine of x that we spend tons of time investigating and taking derivatives of. The fact is, most mathematical objects are just very complicated and unwieldy. But we still focus on the nice ones because, for one, it helps us master the basics, and for two, in the case of something like calculus, well, it may be true that most functions are not differentiable. In the real world, that rare class of differentiable functions do show up as useful models quite often. Back to basics though, if the integers are so uncommon among the number line, what the heck are all these other numbers? They're the fractions, right? Our beloved fractions. Between 0 and 1, there are infinitely many of them. 1/2, 1/3, 1/4, 1/5, and between any two fractions we can find another by just taking the average. The formal term for these beautiful creatures is the rational numbers, the numbers which can be written as a ratio of integers. And the set of all of these irrational numbers is denoted with a cute little q like that. And knowing how there are all these rational numbers lurking on the number line, it seems plausible that they make up most of these chasms between the integers. Of course, we all know there are a few famous numbers that are not rational. Pi, the ratio of a circle's circumference to its diameter, can't be written as a ratio of integers, and so its decimal expansion never settles into a repeating pattern. And the same is true of the numbers e, phi, and square root of 2. And it's not surprising that many would assume these strange numbers that are occasionally given special attention are the exceptions among the real numbers. It may seem that many numbers are integers, most are rational, and a rare few are irrational. But this is simply not so. Once again, the characters we spend most of our time doing arithmetic with, the integers and the rationals, are the exceptions among the number line. Yes, indeed, almost all real numbers are irrational, which means hardly any at all are not. To prove this surprising fact, we need some inspiration from geometry. Geometrically, when we look at the number line, we can see a length of 2 for this interval between 0 and 2. This interval between 1 and 1.5 has a length of 1/2. The idea here is we can take a set of numbers on the number line and measure its length. If our claim that almost all real numbers are irrational is true, how can we put that in terms of the length of a set on the number line? Well, we should be able to consider all rational points on the number line and show that the length of this set is very small. How small? Well, certainly 0 would do, right? If all the rational numbers on the number line put together had a length of 0, well, that's exactly what we would mean by almost all real numbers are irrational. Quite obviously, though, showing that almost all real numbers are irrational by demonstrating that the rational numbers have a length of 0 presents a challenge, because measuring the infinite set of rational numbers isn't nearly so nice and tidy as measuring the length of an interval. With the rational numbers scattered amongst the irrationals, it doesn't really look like what we're measuring is a length, and accordingly, we'll not call it length, opting for the more general term measure. How do we measure the set of rational numbers and hopefully show that it equals 0? Let's say we were able to fit all the rational numbers in an interval of length 1. Then certainly we should be able to agree that the measure of the rationals is less than or equal to 1, because the entire set fits within that length. Or if we had to split things up a bit and were able to fit all the rational numbers in 5 intervals of length 1, then we could conclude the rationals have a measure less than or equal to 5. By bottling up the rationals in intervals, we can put an upper bound on their measure. That's going to be our strategy, but to give you a better taste of the argument before we see it in full, let's discuss the integers. If we're going to show the rational numbers have measure 0, then certainly the integers, which are just a subset of the rationals, must have measure 0 as well. Here's how we prove it. Consider first the positive integers. We can enclose the first integer, 1, in the interval from 1 minus a little bit to 1 plus a little bit. How long the interval is, of course, depends on how big these little bits are. Let's say the length of the interval is some small positive number called epsilon. Hence, the little bits will be 1 minus epsilon over 2, and 1 plus epsilon over 2. And that will make the total length of the interval containing 1 epsilon. We'll enclose the next integer 2 in a similar way. Enclose 2 in the interval from 2 minus epsilon over 4 to 2 plus epsilon over 4. So then this interval containing 2 has a length of epsilon over 2. You might see now why we're doing it this way. Enclose 3 in this interval and so on. The nth positive integer should be enclosed in the interval from n minus epsilon over 2 to the n to n plus epsilon over 2 to the n. This way, the length of the intervals will be epsilon, epsilon over 2, epsilon over 4, epsilon over 8, and so on. If we add up all those interval lengths and factor the epsilon out of each term, we're left with epsilon multiplied by 1 plus a half plus a fourth plus an eighth, and so on. And if you've done any work with infinite series, you know this sums to 2, so the total interval length is 2 times epsilon. And if you're not familiar with the fact that this sums to 2, and you don't believe me, it can easily be verified. Here is the sum, 1 plus a half plus a fourth plus an eighth, and so on. If we double it, we get that 2 times the sum equals 2 plus 1 plus a half plus a fourth plus an eighth, and so on. In other words, 2 times the sum equals 2 plus the sum. We can subtract s from both sides to find that the sum is indeed equal to 2. So with this technique, we've contained the positive integers in infinitely many intervals that combined have a length of 2 times epsilon. And epsilon is just a small positive number. We are at liberty to make it as small as we like. And no matter how small we make epsilon, each interval will still contain the necessary integer at its center. And this is what it means for a set to have measure 0. That it can be covered, we say, by a set of intervals with arbitrarily small total length. 2 epsilon is arbitrarily small because epsilon can be made as small as desired. We'll take the same strategy over to the set of rational numbers, but naturally, for this more complicated set, our notation is going to get a bit more involved. We can simplify things though by just focusing on the interval from 0 to 1. We'll show that the rational numbers in this interval have a measure of 0, and then extend that result to all of the rationals. Now, in this interval, a rational number must have the form a over b, where b is greater than or equal to a, and both of the numbers are greater than or equal to 1. Note that this means b and a can be equal, which means we are including 1 in this argument. However, a can't be 0, so we're going to have to deal with 0 itself later. Now, if we're trying to contain each of these rational numbers in an open interval, how big should the interval be? Each interval is going to go from the rational number minus some distance, say d over 2, to that rational number plus some distance, say d over 2. So then each interval would have a length of d, and we're really just using d here as a placeholder to begin thinking about how long each interval should be. If all of the rational numbers in this space are contained by intervals that have lengths of d, then what would the total of all those interval lengths look like? To add them all up would require a double summation. We need to allow b, the denominator, to go from 1 to infinity, and then for each possible value of b, a, the numerator, needs to go from 1 to b. And so that would look like this. Please forgive my poor penmanship making this sigma so much smaller than that one. Hopefully though, you can see how this double sum is going to consider every rational number in this interval. b, of course, is going to range through every possible denominator from 1 to infinity, and for each denominator, the numerator can be anything from 1 to the value of the denominator. That way we're always staying within this interval from 0 to 1. And again, just for now, we're imagining that every one of those rational numbers is going to be contained in an interval of length, we'll say d. Hence, we're adding up d for every rational number. Now, the inner sum is simple to evaluate. We would just be adding up d b times. So the sum is equal to this. And now we're in a situation that isn't ideal. No matter how small the d is, taking infinitely many copies of it multiplied by b, which is just getting bigger and bigger, is certainly going to make the sum diverge to infinity. So then we're going to need to design these intervals so that their lengths, currently represented by the placeholder d, will cancel out this factor of b. Of course, just canceling out the b isn't enough because it would still leave us with infinitely many copies of some distance being added together, which still would diverge to infinity. So we need to not only cancel the b out, but also have something left over that will add to a finite number once this sum is evaluated. So here's the trick. Of course, we could cancel out that b with a b in the denominator. But if we had 2 factors of b in the denominator, we'd be left with what's called the harmonic series. This doesn't work either, because the harmonic series is known to diverge. But if we had 3 factors of b in the denominator, then we would actually be left with the sum of the reciprocals of the squares. And this is the famous series from the Basel problem. Thanks to Leonhard Euler's 1741 proof, we have the astonishing fact that this series converges to pi squared over 6. So, since this has a finite sum, we're going to be able to make it work for our argument as long as we can just attach an epsilon to it, which represents an arbitrarily small positive number. So finally, how big will our intervals be that contain each rational number? Well, for each rational, a over b will contain it in the interval from a over b minus epsilon over 2b cubed to a over b plus epsilon over 2b cubed. And this way, the length of each interval will be epsilon over b cubed. The epsilon is there as a small positive number that we can make arbitrarily small, and the division by b cubed is going to have the intended effect of making our sum the famous one from the Basel problem. So now we just have to add up these interval lengths for every rational number a over b. Again, this is the double sum necessary to make sure that we hit every single rational number in this interval. It is worth mentioning that this sum will contain an infinite amount of repetition, by which I just mean an infinite amount of intervals containing each rational number. For example, every time a gets to that upper limit of b, we're going to be including another interval that contains the number 1. Every time b is even, a is going to reach a value that's half of b, and so we'll be including another interval that contains the rational number 1/2. Now, we certainly don't need multiple intervals containing each rational number, but doing so is only going to make it more difficult to establish that all of these intervals containing the rationals have a small total length. So, if it doesn't ruin our argument, we're not going to worry about it. Alright, to evaluate this sum, just as before, the inner sum is just adding this up b times. So we're left with the outer sum, and then epsilon over b cubed multiplied by b, which is epsilon over b squared. Then pull out an epsilon. The remaining sum we know equals pi squared over 6, so the total length of all these intervals containing the rational numbers is less than or equal to pi squared over 6 times epsilon. And this upper bound on the total length of the intervals containing all these rationals can be made arbitrarily small because epsilon is an arbitrarily small positive number. It is worth noting though, if any of you are kind of unsatisfied by this argument just because you're maybe not intimately familiar with this series, we actually don't need it for our proof to work. If we just rewind to this step, there is an alternative approach. Indeed, the first term of this series is when b equals 1, and when b equals 1, that first term is just epsilon. So this is less than taking out that first term, and then starting the sum at b equals 2, and then we can make these terms bigger by making the denominator smaller. We make the denominator smaller by replacing one of the two factors of b with a factor of b minus 1. So now we've made this whole thing bigger by just taking out the first term, and then we've made the rest of the terms just a little bit bigger. Now, we can pull an epsilon out of this sum, and by fraction decomposition, the remaining fraction can be written in this way. If you were to get common denominators and combine these two fractions, you would get right back to here without the epsilon. We can go the other way, decompose it, and we get this. Now, this sum, you can tell by writing out a few terms, is very nice. First, we have b equals 2, which gives us 1 over 2 minus 1 minus 1 over 2. This first term is 1, but everything else is actually going to cancel out. Once b equals 3, for example, this is 1 over 3 minus 1, which is going to cancel out with that minus half, and so on. The only thing that's going to remain is this first 1, so 1 times epsilon, so in total, this is less than 2 epsilon. Whether we bound the total interval length by this or by this, we can make them arbitrarily small by making epsilon arbitrarily small. And that establishes that the measure of the rationals in this interval is 0. But what about the rest of them? Well, which positive rationals are we missing? Obviously, we're missing the rationals that are greater than 1. And what form do these rationals take? Well, they are exactly the reciprocals of all the rationals we've already considered. Instead of a over b, they're the rationals b over a, where again, b is greater than or equal to a is greater than or equal to 1. So the smallest such a rational could be is 1 when b and a are equal, but otherwise it will be bigger than 1. Now, since these are just the reciprocals of what we've already dealt with, we can actually construct the intervals that contain them in the exact same way. Each interval containing the rational number b over a will go from b over a minus epsilon over 2b cubed to b over a plus epsilon over 2b cubed. Again, this gives each containing interval a length of epsilon over b cubed, and hence the upper bound on their total length can be calculated in the exact same way, and we would again arrive at 2 epsilon, which can be made arbitrarily small. So we've dealt with the rationals from 0 to 1, we've dealt with the rationals from 1 to infinity, we put an upper bound of 2 epsilon on the total interval lengths that contained all of these rational numbers. We haven't dealt with 0 yet, but of course it's trivial to contain 0 in an interval of length, say, epsilon. And while I can't fit writing them over here, the negative rationals are just mirror images of these rationals, and so could be contained in the exact same way, with upper bounds of 2 epsilon and another 2 epsilon. Our same arguments could be used for all of those negative rationals that are less than -1 and those that are between 0 and -1. And in total, adding all of this up, we arrive at 9 epsilon as an upper bound for the total interval length of intervals that contain all of the rational numbers. Since epsilon can be made arbitrarily small, we have established that the measure of the rational numbers is 0. And hence, as claimed, almost all real numbers are irrational. For example, what's the length of this interval from a to b? Obviously, it's just b minus a, the length of the interval. But the measure of the rationals in this interval must equal 0, because we know the measure of all rationals is 0, which means the irrational numbers in this interval must account for its entire length. The measure of the irrationals in this space is b minus a, which means the real numbers that aren't rational make up virtually all of this interval. Those of you with knowledge of countable and uncountable infinities may be unsurprised by this result, thinking of course the irrationals far outnumber the rationals, because even though there are infinitely many of both numbers, the number of irrationals is uncountably infinite, whereas the number of rationals is a smaller variety of infinity called countable. However, these facts alone do not suffice to establish that the measure of the irrationals must be greater than the measure of the rationals. For example, the Cantor set, a famously strange set created by infinitely removing middle thirds, contains an uncountable infinity of numbers, like the irrationals, but its measure is 0, like the rationals. No doubt we'll discuss this fascinating set in depth another time, but today's message is complete. We often think of irrationals as strange, unique, and particularly interesting, but in fact, they are the overwhelming majority of the real numbers. So if your favorite number is irrational, just know your favorite number isn't actually special, and it doesn't make you cool. What makes you cool is your handsome face and pleasant personality.
Riverside Drive held me up when the first man I loved died, when I could only say I love you through sobs and say I'll miss you. Last time I wasn't talking shells out of the shotguns, someone with a much bigger